So previously we reviewed the basic properties of charge, like the fact that like charges repel each other and unlike charges attract each other. We learned that you can transfer charge from one body to the other by rubbing or touching two different objects together. Now we will understand charges in more mathematical detail, and we will understand some of the important constants which are associated with the interaction of charges with each other. Now, a French engineer and scientist named Coulomb performed some experiments, and using these experiments he was able to discover some curious properties of charge which are similar to another force that you have already learned about. For example, he realized that the electrostatic force, that is the force between two stationary charges, two static charges, is directly proportional to the product of the magnitude of these charges. So if you have two charges, let's say we have Q1 and Q2, the forces between these two charges is directly proportional to the product of Q1 and Q2. He also discovered that this force, this electrostatic force, is inversely proportional to the square of the distance between these charges. So what he discovered is that the magnitude of the force between two static charges is directly proportional to the product of the charges and inversely proportional to the distance between those two charges, to the square of the distance between those two charges. In different terms, if we were to double the distance between two charges, the forces between them would decrease by a factor of 4. If you tripled the distance between two charges, the forces between them would decrease by a factor of 1 upon 3 square, that is by a 9th. Now, if you were to combine these two relationships together, we find that the electrostatic force is proportional to the product of the charges and inversely proportional to the square of the distance between these charges. If we add a constant of proportionality, we get an equality. So F is equal to K Q1 Q2 upon R square. Now you could ask how we were able to determine how much charge there exists on a body, but that is not how Coulomb did this experiment. What he actually did was he was able to backtrack, he was able to measure the forces between charges, and using that information he was able to determine the magnitude of the charges. So in the SI system, K is a constant with a positive value. So its exact numerical magnitude depends on the unit system. In the SI system, K is equal to 9 multiplied by 10 to the power 9 Newton meter square divided by Coulomb square. So this is the constant of proportionality, which tells us what kind of forces two charges interacting with each other will experience. Now here the value of K can be written as 1 upon 4 pi epsilon naught. Let's understand what this means in more detail. So I just said that K is equal to 1 upon 4 pi epsilon naught. Now pi has its usual meaning as it is in maths and physics. So what does this sign epsilon naught stand for? Think about two charges. We have two charges in free space. So here we have Q1 and here we have Q2. You will notice that the formula that we just learned, that is electrostatic force F is equal to K Q1 times Q2 upon R squared, is very similar to another formula for a fundamental force that you learned earlier, that is the force due to gravity. So let's call it Fg, which is equal to G m1 m2 by R square. The two equations are similar. Both have an inverse square dependence on the distance. The role of masses is played by charges and the role of G is played by K. So what this means is that if we have two charges Q1 and Q2 and these charges are separated by a distance R, then the force between them can be calculated. There are two important differences between the gravitational force equation and the electrostatic force equation. Number one is this constant G. If you look at G, G is called the universal gravitational constant, which means that it is same everywhere in this universe. The other implication of G being a universal constant is that if you have two masses m1 and m2 separated by a distance, the force between them is unaffected by the medium between them. So you could have air between these two objects, you could have water between these two objects, you could have interstellar hydrogen between these two objects. The gravitational force between the two masses will not change. And here is an important difference between electrostatic forces and gravitational forces, because unlike gravity, the electrostatic force between Q1 and Q2 does depend on the properties of the medium between them. So the formula that we learn, 1 upon 4 pi epsilon naught is equal to K, in this formula, epsilon naught is a particular quantity that is called permittivity. Most precisely, this is the permittivity of free space, the vacuum, the interstellar vacuum. So what exactly is permittivity? You can think of permittivity as a measure of how much a medium between two charges is affecting the forces between those charges. Remember, unlike gravity, the force between two charges is also dependent on the properties of the medium between them. In fact, this property has been measured to a very high precision for free space, and epsilon naught for free space for a vacuum actually has the value 8.854 times 10 to the power negative 12 Coulomb squares per Newton per meter square. This is the permittivity of free space. The permittivity of air is also very close to this value, so you can use them interchangeably. But this also means that if I change the medium between these charges, if I replace it with some other material, there will be a change in the forces between Q1 and Q2, unlike gravity, where the intervening medium doesn't really matter. Coming back to the original equation, so we know that electrostatic equation for force is equal to K Q1 Q2 upon R square. So we just understood what is the meaning of K, so we can write a more complete equation. F is equal to 1 upon 4 pi epsilon naught Q1 Q2 by R square. Now this equation is giving us the magnitude of the force between two charges. It is not giving us any other information. How can we make this equation more useful to us, more detailed? Well, force is a vector quantity. So it stands to reason that if we define this equation in vector form, it will be more helpful to us. So let's create a simple situation. Let's say that we have two charges placed at 2 points. So this is charge Q1 and this is charge Q2. And if we are dealing with vectors, we need to have some kind of a reference, we need to have some point of origin from which we can measure the distances or displacements of these charges. So let's consider this to be the point O. So this is point O, this is the origin of the coordinate system. And if we were to draw vectors from this point, so I draw two vectors. Let this be vector R1 and this is vector R2. So here we have vector R1 and here we have vector R2. Now if we were to join these 2 points, the positions of Q1 and Q2, all the forces between Q1 and Q2 because of each other will be directed along this line. And we also can derive a expression for the length and direction of the vector connecting Q1 and Q2. So if I were to denote this as vector R21, by vector law we know that R21 is equal to R2 minus R1. So R21 is the displacement vector. It is telling us the displacement between the charges Q1 and Q2. Now the force is being directed along this line. So we can say that if we define two forces, that is F21 a vector and F12 also a vector, I can say that F21 is the force on Q2 because of Q1. On the other hand, F12 is the force on charge Q1 because of Q2. So I can define F21 in vector form as 1 upon 4 pi epsilon naught times q1 times q2 divided by the magnitude of the displacement, that is the magnitude of the displacement between q1 and q2, which we can denote by the expression r21 multiplied by the unit vector r21. Just to refresh your memory, we can define any vector. So I can define r21, the vector r21, the displacement vector, as the product of a unit vector r21. Remember, a unit vector gives you only the direction information. Its magnitude is simply 1, multiplied by the magnitude, the actual physical distance between q1 and q2, that is the scalar value of vector r21. So we have simply defined this force equation in vector form. Conversely, we can also show that R21 is the negative of R12 because R12 is pointing in the opposite direction. So I can show that F12, that is the force on the charge Q1 because of the charge Q2 in vector form, is equal to 1 upon 4 pi epsilon naught Q1 upon Q2 R12 multiplied by unit vector R12. Since R21 is the negative of R12, we can say, infer from this that F12 is equal to the negative of F21. So these two forces are of equal and opposite magnitude, and that does have a significance. Let's see the significance of that statement. First of all, these equations will work for any signs of charges. So if Q1 and Q2 have the same sign, whether they are both positive or both negative, the product of Q1 and Q2 will be positive. So the force between them will be repulsive. If either of the two charges has the opposite sign, then the product of Q1 and Q2 will be negative, in which case the forces between them will be attractive. Next, since we already saw that F12 and F21 are the negatives of each other, we see that the Coulombic force obeys Newton's laws. So, for every action, there is an equal and opposite reaction. For every force, there is an equal and opposite force, and Coulombic forces are obeying that law. And as we already discussed, unlike gravity, the medium between these two charges will affect the forces between them, and those forces, the changes in the forces, are determined by the permittivity of the medium. In standard form, we are dealing with epsilon naught, that is the permittivity of free space, or what would happen if two charges were simply sitting in a vacuum.
Manorama Horizon, learning made simple.